Hi, in this video, we will discuss about the selection of microphone for the free field and the diffuse field. So far, we have gone through the component and the general type of sound level meter. Next, we will discuss about the selection of the suitable sound level meter in various fields such as the diffuse field and the free field. We have learned about the free field condition previously, where you have a point source here, propagate the sound wave in a spherical wave manner. So you can see the sound is propagated in all the directions. If the free field condition is satisfied, we know that when you double the distance away from the point source, then in this case, the sound pressure level will drop by 6 dB. For example, when you are located here, 1 meter away from the point source, so in this case, you listen to the sound and the sound pressure level is equal to 20 dB. When you double the distance away from the point source, let's say here 2 meter, you will listen to the sound, your new sound pressure level will be equal to 20 minus 6, which is 14 dB. Let's say you double the distance again into 4 meter. So let's say here is 4 meter and you listen to the sound again. Then the new sound pressure level will be equal to 14 minus 6, which gives you 8 dB. However, this condition can be only satisfied fully when there are no refracting or blocking objects in the sound path. When there is obstacle in the sound path, part of the sound will be refracted. Part of it will be absorbed and then the remaining will be transmitted through the object. How much the sound is refracted, absorbed or transmitted depends on the properties of the object, such as the sound absorption property, as well as the size of the obstacle and the wavelength of the sound. In general, the size of the obstacle must be larger than one wavelength in order to significantly disturb the sound. For example, assume that we have 10 kHz of the incident sound. How much size of the object that we should design in order to disturb the sound and reduce the transmission? Let's look at this scenario at the top view here. So in this case, your sound source have 10 kHz. The wavelength of the sound is equal to the lambda, which can be computed. The wavelength of the sound, which is equal to lambda, can be computed by using this formula. So we can substitute the F equal to 10 kHz and the C is the speed of the sound at 343 meter per second. So after you perform the calculation, you should obtain 0.0343 meter. And if you convert to cm, you will obtain it to be 3.4 cm. In this case, if we put the obstacle with 3.5 cm, which is greater than the lambda here, the sound will hit to the obstacle and the obstacle will disturb the sound and reduce the transmission sound. However, if we change the sound source to 100 Hz, which is much lower compared to the first case, so when you compute the calculation, you should obtain the lambda is equal to, imagine that you need to build a large obstacle here with the diameter 3.4 meter in order to block the sound from the transmission. From this example, it's much easier to block the sound with high frequency, but it's much more difficult for us to block the sound with low frequency. We can achieve the free field condition at the outdoor where there is no obstacle. For example, if you're standing at the top of the hill here, listening to the sound from the flying object. In this case, the sound from the flying object will propagate to you in the free field manner. To ensure the free field condition inside the room, we need to cover the room with highly absorptive material at the ceiling, floor and also the wall in order to eliminate the refraction. This room is known as an anechoic chamber, which is a sound absorbing room. Inside this room, we want to make sure that there is only one sound source exists, which is the test object that we wish to measure the noise level in terms of sound power, sound intensity level or the sound pressure level. Reverberation chamber or the sound refracting room is opposite to the anechoic chamber. For example, in the bathroom, all the walls and the floor are made by the tiles where the surface are hard and highly refractive. So in this case, imagine you are singing inside the bathroom. The sound will refract in all the directions. So in this situation, we call it to be diffuse field. So bear in your mind, diffuse field is where the sound energy is uniformly distributed throughout the room due to the refraction. Inside the reverberant room, you might see some floating ceiling in order to enhance the diffusion. In practice, most of the sound measurements are made in the room that are neither anechoic nor reverberant, but is somewhere in between them. This makes it difficult to find the correct measuring position when the noise emission from a given source must be measured. For example, in this case, you have a machine that is producing noise, and from the machine you have the direct sound, and when it hits to the wall, it will produce the refraction. When the sound from the machine hits to the floor, it will cause the refraction, and also when it hits to the ceiling, it will cause the refraction as well. Let's label the x-axis to be the distance away from the sound source, and your y-axis is the SPL or the sound pressure level. If this room is an anechoic chamber with free field condition where there is no refraction, so in this case you will obtain the SPL drop 6 dB when we double the distance. However, due to the refraction occurs inside the room, it causes the SPL value to increase near to the machine and in the end of the room. Based on the SPL curve here, we can define this region to be the near field region, which is located around 2 times the machine dimension or the wavelength of lowest frequency produced by the machine. We need to beware that the sound measurement in the near field region should be avoided if possible. On the other hand, if you measure too far away from the machine, for example in this region, the SPL value is equal here due to the refraction. This is known as the reverberant field, and we should avoid to take the measurement in this field. Only the middle region here follow the free field condition, and the SPL measurement should be made in this region. However, in some site measurement, it's quite possible that the conditions are so reverberant or the room is so small that no free field exists. So in this case, we need to apply the standard to perform some correction on the refracted sound. So far, we have learned about the free field and also the diffuse field. In the free field condition, we can use the free field microphone in order to measure the sound. And for the diffuse or the random incident field, we can use the random incident microphone. Bear in your mind, any microphone will disturb a sound field because they tend to be an obstacle to the sound. Free field microphone able to compensate the disturbance it causes in the sound field. Therefore, is suitable to be used in the free field condition. The random incident microphone is designed to respond uniformly to the sounds arriving simultaneously from all the angles. Therefore, it is suitable to measure the sound in the highly reverberant or diffuse sound field. Besides that, we also have the pressure microphone, which responds uniform to the actual sound pressure level, including the pressure disturbance caused by the microphone itself. It is suitable to mount inside a confined zone, such as the duct or the acoustic cupboard. In simple, for the free field condition, we use the free field microphone. For the diffuse field, the microphone need to be as omnidirectional as possible. Therefore, we can use the random incident microphone for the diffuse field. Sometimes, we can use the pressure microphone to substitute the random incident microphone for the diffuse field measurement. This is because both of them have a similar characteristic. In this figure, we have the sound pressure level versus the frequency. We have learned previously that a measurement microphone should have a uniform frequency response. That is, the microphone must have equally sensitive or flat frequency response throughout the frequency range. For example, in this case, the random incident response from the random incident microphone has the largest range of the useful frequency range measurement, followed by the pressure response and also the free field response. Besides the type of microphone, the orientation of the microphone is also important. According to the IEC, if we use the free field microphone in the free field environment here, so in this case, we need to point the microphone towards the noise source. So the angle must be 0 degree, which means you are pointing towards the noise source. If we use the free field microphone in the diffuse field, it will underestimate the actual SPL value. If we don't have the random incidence microphone in this case, you can consider to buy an additional accessory, which is the acoustic resonator that can be mounted to the free field microphone. This acoustic resonator increases the pressure in front of the microphone, especially at the high frequency. By doing that, the underestimated value can be solved. The acoustic resonator can be removed easily. When you wish to measure the sound in the outdoor, which is the free field, then we can just remove the resonator cap and point the free field microphone towards the source. Some sound level meters has the internal incorporated circuit which enable it to switch from the free field response to the random incident response. Therefore, it can be used for these two fields easily. The American National Standard NC requires us to use the random incident microphone for the sound measurement. If we use the random incident microphone in the free field environment here, the angle must be 7 to 80 degrees towards the noise source. If you point this microphone directly towards the noise source, then the measurement will be too high, and this should be avoided. We can select the suitable microphone based on this flow chart. First of all, we ask whether we need to comply with standard or not. If the answer is no, then we need to continue identify the type of sound field, whether it is free field or diffuse field. If it is diffuse field, then we need to choose the random incident microphone for the sound measurement. By doing this, we can obtain the optimum accuracy. No angle restriction for this case. If you point the random incident microphone at any angle at the same point, then you should obtain similar result. If the environment is free field, then we need to use the free field microphone, and we need to ensure the microphone is always pointed toward the noise source at 0 degree. By doing this, we can obtain the optimum accuracy. What if the sound measurement needs to comply with the IEC standard? It's compulsory to use the free field microphone for the IEC standard. If the environment that you wish to take the sound measurement is free field, then we just follow the previous procedure. However, if the environment is a diffuse field, the usage of the free field microphone will underestimate the sound pressure level. Therefore, we need to implement the acoustic resonator in order to compensate this situation. If we need to comply with the NC standard, then it's compulsory for us to use the random incident microphone. This type of microphone has the optimum sound measurement accuracy in the diffuse field environment. However, if you want to use the random incident microphone for the sound measurement in the free field, in this case, you need to point the microphone at 7 to 80 degrees towards the noise source. If you point the microphone beyond this range, then the accuracy of the measurement will be largely affected. When we are taking the sound measurement, both operator and the instrument will interfere with the measurement. Both the instrument and the operator body will block the sound and refract the sound towards the microphone. Experiment shows that the refraction from a person may cause the error up to 6 dB when you are measuring the sound at frequency around 400 Hz. So this happens when there is refraction and you hold the sound level meter less than 1 meter away from you. To avoid the refraction from the sound level meter, is designed in such a conical shape. This design helps to refract the incoming sound to other direction instead of refract it back to the microphone. To minimize the refraction of the sound from the operator body, it is usually sufficient to hold the sound level meter at the arm's length. You can check whether your presence is influencing the meter reading by let the sound level meter remain fixed while you move from side to side. For more precise measurement, we can consider to use extension rod or extension cable to realize the remote microphone. In summary, proper design for the sound level meter as well as proper distance away from the sound level meter is needed in order to avoid the refraction for better measurement accuracy. Sometimes we use the sound level meter together with a special windscreen consists of a ball of porous sponge. It helps to reduce the noise generated from the wind. Besides that, it can also seal the microphone from the dust, dirt, precipitation as well as the mechanical damage. In terms of the relative humidity levels up to 90%, it will have a negligible effect on the sound level meter. Care should be taken to seal the instrument from the rain, snow, and etc. For continuously use the microphone in extremely humid environment, it is recommended to use the rain cover or the dehumidifier. Some microphone that is designed specially for the outdoor environment can be considered as well. Most of the sound level meter designed by the BNK can operate accurately from -10 degrees Celsius to 50 degrees Celsius. Sudden temperature change will cause the condensation inside the microphone. Extra care should be taken to avoid this. The microphone sensitivity can be remained as long as the ambient pressure variation is around ±10%. If we wish to take the measurement at high altitude, the microphone sensitivity might be affected. In this case, we need to check the microphone instruction manual carefully to see if it is suitable for this application. Pistol phone is the instrument that we use to calibrate the sound level meter. When we are performing the calibration, the correction must be made for atmospheric pressure. Although microphone and the sound level meter are relatively insensitive to vibration, however, it is still recommended to isolate them from strong vibration. For high vibration environment, we can consider to use the rubber pad or similar isolating material for the sound level meter. Lastly, the influence of the electrostatic and the magnetic fields on the sound level meters are negligible. If we wish to take the measurement for the environment noise, then we need to take the measurement of the total noise at a particular location. That is irrespective to its noise source. Noise at an employee's workstation is an example for the environmental noise. The noise received by the employees might be directly coming from the machine 1, 2, 3, and so on, as well as the refraction on the wall, ceiling, or the floor. The measurement is made based on where the person is working, without regard to whether they are in the near or far field of their machines or whether other machines are operating nearby. As you can see, the environment noise comes from various directions, therefore the sound level meter should be omnidirectional. In this case, random incident microphone is useful because it fulfills this requirement. These are the other examples for the environment noise. We have learned how to use this formula previously to obtain the actual sound pressure level from a machine by subtract the total environment noise with the background noise. For example, if the environment noise is measured to be 60 dB, if you turn off the machine 1, then you obtain the remaining background noise to be 53 dB. After you perform the calculation, you should obtain the answer to be 59 dB. This is the sound pressure level from the machine 1 only. We can also use this table to compute the noise from the machine. The total noise is 60 dB, background noise is 53 dB, similar to the example here. Then the difference between the total noise and background noise is 60 minus 53 give you 7 dB. From the chart here, based on the 7 dB, we have 1 to be the correction. Therefore, we need to correct the total noise and subtract 60 dB with the correction value here. By doing that, you obtain the final result to be 59 dB, and this is the noise of the machine. Both methods give you the same result. In this example, when the gear motor is running, the other machine is working as well. So in this case, we measure the sound pressure level by using the handheld sound level meter here. From this measurement, the total sound that you measure is equal to 77 dBA. Then you continue to turn off the gear motor and perform the sound measurement again. And you get 73 dBA, and this is about the background noise. Then we can substitute the total noise and the background noise inside this formula. After you calculate, you obtain 74.8 dBA. So this is the sound pressure level produced by the gear motor alone, without the effect of background noise. We need to be careful when we use this formula to exclude the background noise effect. If the total between the total noise and the background noise is at least 10 dB and above, then in this case, the measurement will be valid. This calculation is accurate within 0.5 dB. If the difference between the total noise and the background noise is within 3 to 10 dB, so in this example the difference is 5 dB, which is within this range, in this case the calculation is still valid. However, if the difference between the total noise and the background noise is less than 3 dB, for example in this case the difference is only 2 dB, then the calculation that we obtain here will be invalid. This is because the source noise from the machine is lesser than the background noise, which is non-logic in actual. As a rule of thumb, if the measurements are made in the frequency bands, the background noise measured in each band should be at least 3 dB lower than the noise source as well. In this example, you have two machines operating simultaneously. Machine 1 produces the sound pressure level equal to 82 dB. Machine 2 produces sound pressure level equal to 85 dB. The difference between machine 1 and 2 is 3 dB, and from this chart, we can see at 3 dB, the correction is equal to around 1.7. Therefore, you take the largest value plus the 1.7, it gives you the total noise produced by machine 1 and 2 is equal to 86.7 dB. If you use this formula to compute the summation of the sound pressure level by let the L1 equal to 82, L2 equal to 85, then you obtain the total sound pressure level to be this answer as well.